22 disasters accounting for losses in excess of $1 billion each. That's a new record.
Hurricanes, storms, and wildfires are forcing Americans to abandon their homes.
Europe's weather has gone crazy this summer.
Hi, and welcome back to the final episode of this virtual field lab series, where we have been investigating climate feedback loops and changes in the Earth's energy balance. I'm Mikhail Thompson, an architecture student at Washington University in St. Louis, and your climate host for this series. The changing amount of energy being absorbed by the planet is impacting the frequency and intensity of wildfires, floods, hail, and other extreme weather events. As an architect, these factors play a huge role in how we think about designing homes and cities for a future with a warmer, more extreme climate. In episode 1, we investigated how decreasing sea ice around the North Pole is drastically increasing the amount of solar energy being absorbed by the planet. In the second episode, we investigated the growing number and size of energy-absorbent melt ponds on the surface of the Greenland ice sheet. Both of these changing environments were being impacted by feedback loops driven by increasing atmospheric greenhouse gases like carbon dioxide and methane. On the hopeful side, Alden did identify ways that we can break these feedback loops by rapidly moving to a future powered by new, cheap, clean energy alternatives. For the first time in human history, we actually have the opportunity to choose clean, inexpensive energy systems like wind and solar. If we do make this clean energy choice, then it will be up to architects like me, along with engineers and city planners, to begin to design and build new homes and cities that support a sustainable future. In this final episode, we're going to travel back to the Greenland ice sheet to see how even smaller, microscopic changes taking place in the snowy surface may be impacting the balance of energy on our planet. Thanks for joining me for this series of investigations. Let me turn you over one more time to Dr. Alden Adolph, a climate scientist from Michigan Technological University. She's an expert in the physics of snow and ice, as well as the changing energy balance of our planet.
Hi, I'm Alden Adolph, a climate scientist that studies how changes taking place in snow and ice are impacting the energy balance of the planet. My specialty is albedo. That's the measure of how much energy a surface reflects. In episode 1, we looked at Earth's energy balance on a global scale. We explored the changing ratio of sea ice and open ocean around the North Pole, as well as rising carbon dioxide levels. In the second episode, we zoomed in a bit, looking at melt ponds on the surface of the Greenland ice sheet. We looked at how increasing methane levels are contributing to the rapid warming we're all experiencing. So far, we've focused on big changes across the planet's surface. In this episode, we're going small, down to the microscopic level, to see how tiny changes in surface snow and ice crystals might also be impacting the Earth's energy balance. These surfaces may not be melting, but they are being exposed to gradually increasing temperatures as the planet as a whole warms. The first thing we'll analyze is how very small changes in the grain size of snow may be affecting the amount of energy absorbed by the Greenland ice sheet. Let's write this question down in your notebooks. How does the grain size of snow impact the amount of energy absorbed? Now I'll hand it over to Amy, who will guide you through this investigation. When you're done, I'll meet you back here to talk more about how even microscopic changes in snow and ice could be influencing the planet's energy balance.
Thanks, Alden. I'm Amy, a senior at Grant High School in Sacramento, California. Alden asked if I could help investigate how changes in the grain size of snow impacts the amount of energy absorbed. No problem. First, I think we need to explain what we mean by the grain size of snow. When you think of snow, you may think of the classic hexagonal dendrite form, like this image, taken by the famous snow scientist Wilson Bentley. A lot of the snow does fall in that form, but it can also fall in other forms, such as all of these different types of snow. After the snow hits the ground, things become even more complicated. Snow begins to metamorphose or change as it ages and is exposed to things like temperature changes, sunlight, wind, and humidity. Some of these factors cause the grains of snow to grow. You can see that in this video made by a snow scientist named Martin Schneebeli. His video shows how the grains of snow grow over time. We measure the size of the grains of snow in millimeters. The question Alden asked us to investigate is, how does the grain size of snow impact the amount of energy absorbed? To answer that question, we'll need to find data that includes both the size of the snow grains and data that shows how much energy is absorbed. Fortunately for us, the European Space Agency has a satellite that's been collecting exactly this kind of data. Here's a picture of the Copernicus Sentinel-3 satellite. As the satellite orbits the planet, it collects data on the grain size of snow as well as the albedo of the surface. Since the albedo is a measure of the amount of energy absorbed, these two measurements would allow us to see if there is a relationship between the size of the snow grains and the amount of energy absorbed. Let's make a data table in your notebooks to record the snow grain size and albedo. We'll start by measuring the size of the snow grains across the Greenland ice sheet. Here's an image showing the size of the grains of snow across Greenland's ice sheet. We'll zoom in on one area of the ice sheet that has continuous data across the entire surface. The ruler will allow us to take consistent, evenly spaced measurements. The color-coded scale on the side can be used to estimate the grain size of the snow at each whole number along the ruler. For example, I would estimate that at the 0 mark, the color on the scale matches at a grain size of approximately 1.7 millimeters. Since we're estimating, our values may be slightly different, but we should be in the same ballpark. Next, pause the video and estimate the size of the snow grains across the Greenland ice sheet at each of the whole numbers on the scale. When you're done, hit play again, and we will move on to the measure of the albedo at each of the same locations. Welcome back. Some of those estimates were not easy to make. Here are my best estimates for each of the locations. Hopefully our numbers are similar. Next, I'll bring up another false color satellite image of the Greenland ice sheet that shows albedo. We'll zoom in at the exact same locations and the exact same scale. This time, the color-coded scale will be used to estimate the albedo of the surface at each of the numbered locations. Let's make the first measurement together. At the 0 mark, I would estimate that the albedo of the snow surface is approximately 0.40. Remember, an albedo of 1 means that 100% of the energy that hits the surface is reflected. The lower the albedo number, the less energy is reflected and the more energy is absorbed. Pause the video and estimate the albedo of the Greenland ice sheet at each of the other whole numbers on the scale. When you're done, hit play again and we can talk about the best way to analyze and graph the data. Welcome back. I found the albedo measurements were even harder to make than the grain size. Here are my estimates for each of the sample locations. I always think data like these tell a better story when displayed and analyzed on a graph. Transfer your data to your graph, then I would like to ask you to do 3 more things. First, estimate and draw a best fit line through the data. Next, if you know how to calculate the slope, finish your analysis by calculating the slope of the best fit line you drew. And third, write a sentence describing what you think data suggests about the relationship between albedo and the size of the grains of snow. Welcome back. Here's what my data looked like when they were plotted on the graph. I thought the data looked fairly linear, so it was pretty easy to draw a straight best fit trend line through the data. I picked 2 spots on the line to calculate the slope. My rise in albedo was 0.38 on the y-axis, and the run was 1.4 millimeters on the x-axis. These numbers gave me a slope that suggests that every 1 millimeter of grain growth caused the albedo to go down by 0.27. I love how calculating a slope really helps understand and tell the story of the data. Let's look back to where we started this investigation. Alden wanted to know how microscopic changes in the size of the grains of snow impacted the amount of energy being absorbed. In this investigation, we did measure the grain size, but didn't measure energy directly. Instead of energy, we measured the albedo of the surface. Let's add a couple notes to our graph to better connect our albedo measurements to Alden's question. If you remember from the first 2 episodes, the albedo scale goes from 0 to 1. Surfaces that are closer to 1 on the albedo scale reflect most of the energy that strikes them. Surfaces that are lower on the albedo scale absorb most of the incoming energy. Let's add these 2 notes to your graph. After you add those notes, then respond to our investigation question by writing 2 things that you notice and 1 thing that you wonder. When you're done, hit play again and Alden will be back to wrap up the episode.
Welcome back. The slope calculation that Amy showed tells us that for every millimeter a grain grows, the albedo dropped by roughly 0.27. This is a useful approximation, but it assumes that the only thing affecting albedo is how big the snow grains are. In reality, there are other factors that also lower snow albedo, like when snow is dirty with soot or dust, or when the snow is wet. Even still, it's useful for us to see how these microscopic changes to the snow can lower the albedo, causing more solar energy to be absorbed. Over the last 3 episodes, we've explored how Earth's energy balance is being disrupted by both large-scale and microscopic changes in snow and ice. In episode 1, we looked at how rising levels of carbon dioxide are warming the planet and accelerating the loss of Arctic sea ice. In episode 2, we saw how warming temperatures are causing surface melt ponds to form on the Greenland ice sheet, further reducing reflectivity and increasing energy absorption. In this episode, we learned that even something as small as the grain size of snow can make a difference. As snow warms, the grains get larger, which reduces albedo and causes the surface to absorb more energy. These tiny shifts can speed up warming even before melting begins. All of these changes form what we call climate feedback loops, self-reinforcing cycles that can accelerate warming. Humans initiated these changes in the Earth's energy balance by developing an energy system based on fossil fuels. But here's the hopeful part. For the first time in history, we have the technology available to begin to slow and even break these feedback loops by choosing to move to renewable energy alternatives like wind and solar. These new technologies now provide the cheapest energy available and reduce the greenhouse gases that drive the warming feedback loops. By lowering emissions, we can help preserve high albedo surfaces like snow and ice, protect Earth's natural cooling systems, and stabilize the energy balance of the planet. So, while the feedback loops are powerful, they're not unstoppable. Every action we take now, no matter how small, can help steer us towards a more sustainable and resilient future. Thanks for taking time to explore albedo, feedback loops, and Earth's energy balance with me. I hope you learned something new and maybe even feel a little inspired. Each of us can and must be a part of the shift to cleaner, cheaper energy that helps restore the balance of energy on our planet. It's a big challenge, but I believe that together we can build a better, sustainable future.
I always mess up the Greenland ice sheet. On the hopeful side, Alden did identify. Why am I struggling with the word identify? And the first, oh,